All right, people are slowly connecting, so I think we can get started. Hi everyone, welcome to this second seminar of the Clever Planet Fall 2022 seminar series. My name is Maxime Maurice, I'm a postdoc at Rice University, and I'm your host for today. And before I go on and introduce you our speaker for today, we'll proceed to our little ritual, which starts with me telling you a few words about the Clever Planet project, which is, let me change slides. Yeah, here it is, which is organizing this seminar series. So the Clever Planets project is a multi-institutional and interdisciplinary initiative to unravel the conditions of planetary habitability in the solar system and beyond. Its lead institution is Rice University, and it is supported by NASA as one of the teams in Nexus for Exoplanetary System Science, also known as Nexus Coordination Network under astrobiology. And then we have this land acknowledgement, where we acknowledge that our research at Rice University is pursued on the traditional lands of several native peoples, namely the Karankawas and Sanas, as well as the Coahuiltecan, represented today by the Tapilam Coahuiltecan Nation, and the Ishaks, represented today by the Atacapa Ishak Nation. We see it as our duty to acknowledge this historical aspect of our identity and to foster a beneficial environment for all communities, in particular those who preceded us on this land. And with that, that's my great pleasure to introduce you our speaker for today, Professor Joshua Krissansen-Totton. So Josh is a specialist of habitability of the Earth, of the planets, but also of exoplanets. And in particular, he's developing models to try and predict under which conditions habitability can emerge, but also to try and discriminate between biosignatures which could indicate habitability on other worlds. So after his studies in his undergrad in New Zealand, Josh came to University of Washington in Seattle, where he did his PhD. And he then moved to a little bit south to the lovely campus of UC Santa Cruz, where he did a postdoc as a NASA Sagan Fellow. And since the beginning of this semester, he is now an assistant professor back at his grad institution, University of Washington in Seattle. And so, yeah, with that, Joshua, the floor is yours. Take it away. We are looking forward to your talk.
Hey, thank you for that introduction, and thank you all for being here. Let me just get set up. All right, hopefully that's all still working.
Yes, it is.
Okay, great. This, as Maxime mentioned, I recently started as an assistant professor at the University of Washington, but most of the work that I did, that I'm going to be talking about today, was done during my postdoc at UC Santa Cruz with collaborators both at Washington and Santa Cruz, and I'll highlight the contributions of a couple of really wonderful students as we go. All right, so to motivate this, I think it really is true to say that the capabilities to characterize terrestrial exoplanets are imminent. This image down the bottom here is the latest webcam image from the ELT construction site. You can see they're well on the way to building the dome here. And then, of course, the James Webb Space Telescope has already started observing terrestrial exoplanets. I think all those data, none of those data are public yet, but this is happening right now. We're finally getting information on the atmospheres of potentially habitable terrestrial exoplanets. And then, of course, as I'm sure you're all aware, the Astrophysics Decadal Survey released last year prioritized a flagship mission, a space telescope for a flagship mission that would be purpose-built to go after biosignatures, atmospheric biosignatures, signs of life on terrestrial exoplanets using reflected light spectroscopy. And so this is something to look forward to in the slightly longer term. But as I'm sure you can all attest to from your sort of individual areas of expertise, there's a possible difficulty here in that planets are immensely complicated. How do we actually confirm life from these astronomical observations? How do we distinguish planetary processes from the influence of biology? And this is an area where the toolkit of the astronomer will get you to a certain point, but really trying to understand the way in which whole planets operate is going to be crucial. And I appreciate that I'm probably preaching to the choir here to some extent. There's a lot of this kind of science coming out of the Clever Planets collaboration, and this slide is just a few the highlights of that kind of thinking. But this is hopefully a good lead into what I want to convince you of today, is that testable and ultimately tested theories of rocky planet evolution are going to be needed to distinguish lifeless planets from inhabited worlds, to try and anticipate the products of whole planet evolution for lifeless planets, and clearly distinguish those from the influence of biology. So within that theme, we'll first chat a little bit about oxygen as a biosignature, oxygen false positives, and how models of whole planet evolution can be helpful here. We'll then talk about the related subject of Venus, why there isn't oxygen in Venus's atmosphere, trying to constrain the possible past habitability of Venus. And then, having applied this model to Venus, we'll then try and extrapolate to some of these eminently characterizable terrestrial exoplanets to make some sort of crude predictions for what we might see there. And then I'll try and tie it together at the end. So, beginning with oxygen then, oxygen is, of course, a very well-studied biosignature, and the reason that people think of oxygen as a potentially promising exoplanet biosignature is more sophisticated than just an argument by analogy. It's not just the case that, oh, there's all this oxygen in the air produced by plants, that look for that elsewhere. You can additionally make a fairly compelling evolutionary argument for oxygenic photosynthesis being widespread, even if biochemistry elsewhere is radically different to that of the Earth. Oxygenic photosynthesizers are going to have an advantage over other sort of chemoautotrophic ecosystems or anoxygenic photosynthesizers, and that the substrates required are virtually unlimited. And so there is this evolutionary payoff from oxygenic photosynthesis, which sort of motivates the search for oxygen elsewhere. Additionally, though, it's generally been thought difficult to maintain oxygen-rich atmospheres purely through lifeless processes. And there's a lot of work on this. This is a figure from one of Vicky Meadows' review papers on this topic, outlining the different scenarios proposed for how you might obtain oxygen-rich atmospheres without life, and how you might, what are the other observations you could make that would discriminate that from genuine biological oxygen. For the most part, though, these scenarios are they're most problematic for planets around low-mass stars, owing to their particular distinctive photochemical environment, the distinctive stellar spectrum, and distinctive stellar evolution. And so I got interested in the general tendency of rocky planets to oxygenate their atmospheres, regardless of host star type. I wanted to know sort of how common was this, that you would potentially have oxygen-rich atmospheres without life. And to get at this, you really need a model of whole planet evolution, as I alluded to earlier. And so this is just going to be a schematic explaining the features of the model we developed to do this, to capture planetary redox evolution. And so the goal here is to try and model redox evolution from the magma ocean origins through to a planet's more temperate evolution. And so to begin with, we're tracking hydrogen escape, oxygen accumulation. So you dissociate water, preferentially lose the hydrogen, oxygen gets left behind to potentially oxidize the magma ocean as it freezes. Subsequently, you may still lose hydrogen to space, net oxidizing the planet, but in this more temperate state, you have to keep track of these crustal sinks for oxygen, so things like degassing, water rock reactions. And so we wanted to tie this together in one continuous evolution. Of course, to keep track of these oxygen sinks, you need to keep track of the thermal state of the planet, since that's dictating magma ocean solidification, as well as the surface climate, since a lot of these crustal oxidation processes are somewhat temperature dependent. So there's a radiative convective climate model built in here. But of course, to know surface climate, you need to know where the other volatiles are. And so we're attempting to track how CO2 and water partition as we evolve from this magma ocean to a more temperate state. And so this very much builds on the heritage of other planetary redox evolution models. The other thing I should mention about the model, as you can imagine, there are many uncertain parameters here in not only initial conditions, but also how does the star evolve, how does atmospheric escape work, how does the carbon cycle operate, how efficient are these crustal sinks for oxygen. So to try and accommodate that, we take a Monte Carlo approach where we sample all these unknowns, and then every model output that you see will be some ensemble of outputs across all those uncertain parameters. So just to give you a sense for how this all works and how these different parts of the model tie together, this is the model applied to just the Earth through time. And this is a lifeless Earth because we're interested in the tendency for rocky planet atmospheres to become oxygen rich without life. And so I'll break down what we're looking at here, but this is a whole bunch of time evolution plots for this Earth. The x-axis is time in years. And so we'll start off with the thermal evolution here. This is the evolution of mantle potential temperature and surface temperature. You see the magma ocean lasting a few million years before the surface cools off. You can also see that here in the evolution of the solidification radius as it moves from the core mantle boundary to the surface after a few million years. And then atmospheric composition is co-evolving with this interior evolution. So we're tracking oxygen, CO2, and steam in the atmosphere. Much of this behavior is driven by the planetary energy budget. And so here you'll see the outgoing long wave radiation. Oh, I should get my laser pointer here. Well, can you see my cursor or no?
Yes, we see it.
Oh, great. Okay. So after a few million years, or I should say, it takes a few million years for the outgoing long wave radiation, blue here, to drop below the runaway greenhouse limit. And when that occurs, that is when the magma ocean is ending. That's when the previously steam-dominated atmosphere condenses out, so atmospheric water drops and forms liquid or solid water on the surface. This is average ocean depth in kilometers. You can see it condensing out there after a few million years. And of course, once you have liquid water around, you can then temperate carbon cycle, or outgassing and silicate weathering are modulating climate evolution. And we're of course keeping track of the post-magma ocean crustal production, since this is going to be really crucial to our crustal sinks for oxygen. And all of this is done to track the evolution of the planetary redox budgets. On the right here, this is atmospheric sources and sinks of oxygen, oxygen sources from hydrogen loss, and then crustal sinks for oxygen. And then we're also tracking the mantle redox state across this evolution. All right, so that's the model applied to Earth. And you might be wondering at this point, why should we trust this complicated model with all these moving pieces? And there's, of course, I don't want to oversell this in the sense that this isn't meant to be the finished theory of planets. This is a collection, or at least I think of this as a collection of stories we tell ourselves about how planets work, based on our understanding of the solar system. And this is an attempt to tie together these stories to be able to make some, to see if they're self-consistent, and to make some self-consistent predictions that can then be tested against reality. With that said, I think it is at least reassuring that the model does recover the correct values, the true state of the modern Earth, and that it's roughly the right thermal state, the right crustal production, atmospheric composition, fluxes of carbon, and so on. And of course, part of this is by design, but I think it is reassuring to see that this is a self-consistent story. And you can also attempt to validate the model at a more granular level. So you can take, say, the outgassing component of the model, predicted fluxes of different volatiles, and then compare that to observations of volcanoes, the same kind of region of parameter space. And I should say the outgassing model is built by Nick Wogan, a student I worked with at the University of Washington. He built this really fantastic model of planetary outgassing. And so you do that comparison, things look pretty consistent to first order. The redox evolution component of the model is also very much motivated by other work we've done looking at the oxygenation of Earth's atmosphere through time, sources and sinks of oxygen into Earth's atmosphere. So all of this is, at least we have attempted to ground it in what we think we know about Earth evolution. So this is what the lifeless Earth evolution looks like, and most importantly for us is this atmospheric composition evolution. What we find after 4.5 billion years, you consistently get that the atmosphere, in the absence of life, should be oxygen free. The oxygen here in green is essentially zero. This is good news, right? For oxygen as a biosignature. It's saying for a literal Earth twin, the Earth around the sun, you don't expect oxygen to accumulate in the absence of life. Perhaps not too surprising, but what was surprising was that when we started to change the initial conditions a little bit, change the initial volatile inventories, for instance, we found it was possible to, for an otherwise Earth-like planet around a sun-like star, to obtain a very oxygen-rich atmosphere without life. And I won't go into too much detail here, but just to give you a flavor of what that looks like, we'll talk about one of these three scenarios, the water world case. So this is exactly the same calculation as I showed you before, but now we've endowed our Earth around the sun with tens to hundreds of Earth oceans. So when the magma ocean ends, you condense out perhaps a few hundred kilometers of liquid water at the surface. And so the immense pressure from this surface water increases the solidus, the crust, which has the effect of pretty rapidly shutting down the production of new melt. As you can see in this plot of crustal production, it tends to zero after 1 billion years or so, and this effect has been described previously. But there's consequences for the redox evolution. If you shut down crustal production in this way, you shut down your sinks for oxygen. So a very slight source, a very slight leakage of hydrogen into space is potentially enough over billions of years to leave behind very oxygen-rich atmospheres. And that's what you see in green here. After a billion years or so, oxygen may start to accumulate. But you also see that in this figure, every dot is an individual model run. And we're plotting final oxygen versus how much water you started with in Earth oceans. A few Earth oceans, there are no problems, but as you get up to tens to hundreds of Earth oceans, very oxygen-rich atmospheres become a probable outcome due to this sink suppression. And in the paper here, we talk about observations you could make to try and distinguish this kind of oxygen false positive from genuine biological oxygen. But this is just one example. These types of models are useful more generally to try and investigate the likelihood of non-biological oxygen as a function of stellar age or stellar type, or in this case, planet-star separation. So this is a movie put together by Max Galloway, a former student at Santa Cruz I work with now at UCF. So in this movie, we'll see a whole bunch of planets from 0.7 to 1.3 AU around the sun. And we're tracking their atmospheric oxygen on the left, CO2 in the middle, and steam, water vapor on the right, as well as the temperature, surface temperature, which is the color bar. We start off in the magma ocean, but as you see, after a few million years, you cool off. The vertical dashed line here is the runaway greenhouse limit creeping outwards as the sun is getting brighter. And so exterior to that, you do see a number of planets that in the habitable zone, but have very oxygen-rich atmospheres due to non-biological processes. So work is ongoing to try and understand the interesting trends here in atmospheric composition. But I wanted to focus your attention, so obviously you can imagine how these sort of statistical predictions might be useful for the future direct imaging missions. But I wanted to pause the movie at 4.5 billion years here and draw your attention to Venus-like separations. So at 0.7 AU, you see that there are a number of model runs, number of planets that look a whole lot like Venus, which is to say they have virtually no atmospheric oxygen, 100 bar-ish CO2, virtually no steam. But there are also a fairly large number of model runs where you get very different looking atmospheres that are not consistent with Venus, that perhaps have a lot of oxygen or water vapor or both. And so in my mind, it's a really interesting question as to why Venus ended up looking like it did and not like these other seemingly just as self-consistent outcomes. And I think if we want to understand, if we want to use oxygen as an exoplanet biosignature, we would like to understand why Venus did not end up with a lot of oxygen in its atmosphere, despite seemingly have lost a lot of hydrogen to space. So in my mind, understanding Venus evolution is really a prerequisite to using oxygen as a biosignature. There are, of course, many other intrinsically interesting questions one can ask about Venus, particularly on the limits to habitability. Is it possible that Venus was habitable earlier in its history? And there's conflicting views on this. It has been shown with 3D climate models that it's possible to have maintained a temperate climate state early on due to Venus's slow rotation. You get a lot of cloudiness at the sub-solar point, increasing planetary albedo and keeping the surface in a stable temperate state. This has been challenged, though, by other 3D models that show that while this may be true on the left, it might be difficult to transition from initial hot steam magma ocean atmosphere to this temperate state because you start off in this configuration where it's too hot on the day side for clouds, and so you're absorbing a lot of radiation. Clouds on the night side trap heat, and so you're sort of trapped in this hot state. So there's still work to be done here to really explore this parameter space. of course, there's also evidence from the geology and geomorphology. It's been known for a long time that there are these tessera regions on Venus, seemingly the oldest parts of the crust, very highly deformed tectonically. Some tentative evidence of felsic crust in these regions. And there's even been claims that the geomorphology here is, or in some places in the tessera, is consistent with past fluvial erosion. The features here are, by analogy, argued to be produced by fluvial erosion. On the other hand, it may be possible to explain these features with aeolian processes. They may not be sedimentary rocks, and so this is still an open question. More broadly, it's always been difficult to reconcile recent habitability with the lack of oxygen in Venus's atmosphere, and that if you want to have had a Venus that was habitable recently, you have to explain not only how you got rid of the water so quickly, but how you got rid of the oxygen left behind from hydrogen loss. And Cedric Gilman has worked on this really extensively. So I got interested in this question and whether applying our model of whole planet evolution to Venus could shed some light on the fate of oxygen and the possibility of past habitability. And so, skipping over a lot of details, this is what it looks like applying the model to Venus. You don't actually have to change much in the model to get things to work for Venus. It's essentially the same, just a different planetary separation and size. I did add a few bells and whistles, added argon-40 and helium to the model as traces of sort of cumulative outgassing and recent outgassing, respectively, as another test for self-consistency there. But otherwise, this is a very similar model to the Earth model from before. What you find is that there are two distinct scenarios for recovering modern Venus, as shown here. So there are a number of model runs where you can recover the modern Venus state with no period of habitability. And so you transition directly from this hot magma ocean atmosphere to the current runaway greenhouse with nothing in between. You never condense water on the surface. And the atmospheric evolution just looks like gradual hydrogen loss, the oxygen being mopped up by crustal sinks. And you're left with the CO2-dominated modern atmosphere. There are also, though, a number of model runs. We get to the same endpoint with a period of habitability on early Venus. So see that here, you transition from the early magma ocean atmosphere to a temperate surface of order 1 billion years before going back into runaway greenhouse. And during that habitable time, you have perhaps 100 meters of globally average ocean depths. The CO2 gets drawn down before degassing again as you go back into runaway greenhouse, and the remaining oxygen and water is mopped up. So those are the two ways that you can get to modern Venus. And then, of course, what you can then do is take all these model outputs and ask, well, what must be different between these two cases? What explains the difference? And that I won't go through every detail in this figure, but this is essentially what we're trying to do here, is looking at in purple are the model runs that were never habitable, the left-hand column from the previous slide. The yellow are the right-hand column, the model runs that did have a period of transient habitability. And in the cyan dots are model runs that just didn't successfully reproduce the modern Venus atmosphere. So just to take a look at some of these figures, this is plotting, and this one should be fairly intuitive. We're plotting albedo, initial water inventory. We're not trying to model cloud feedbacks, we're just assuming an albedo and looking at the consequences for that. So of course, never habitable model runs in purple, albedo tends to be lower, whereas Venus, if you want Venus to have had a habitable past, you have to have had a higher albedo in order for the surface to be temperate. But you also find this negative correlation with initial water inventory for the habitable cases. And that is because if you want to have had a larger endowment of water, you must have had a low albedo to ensure that you went back into runaway greenhouse long enough ago for enough time to have elapsed to have lost all the water since. You can see the same thing if you plot max ocean depth versus albedo. The never habitable cases, of course, didn't have an ocean by definition, but for these yellow habitable runs, deeper oceans in the past require lower albedos. Another interesting plot is this final oxygen versus what we've called dry crustal oxidation efficiency. So this is like a kind of a catch-all for oxygen sinks that are not kind of the obvious sinks that you think of, so things that are not the outgassing of volatiles or water rock reactions. So this could represent the direct dissolution of oxygen into surface lavas. It could represent reactions with supercritical phases, solid gas phase reactions. Whatever it is, we find has to be fairly efficient in that both habitable and never habitable scenarios require this efficient source of crustal oxidation, whereas if you don't have it, you tend to leave behind 10 bar of oxygen in the atmosphere, inconsistent with what is observed. Now, for the most part, the model doesn't strongly favor a habitable or not habitable history, but with one possible exception. If you account for the fact that having a really CO2-rich atmosphere, a CO2-dominated atmosphere, if you believe that that's going to radiatively cool the upper atmosphere and throttle water loss by just reducing the amount of water that gets into the upper atmosphere, you find that it's actually quite difficult to get to modern Venus without a period of habitability. And the reason for that is shown in this movie. So I'll start it in a moment. This is just a whole bunch of model runs plotting CO2 versus water versus oxygen is the color, and the square model, the square symbols represent past Venus that was habitable. What you find is that in that habitable epoch, you draw down atmospheric CO2, you sequester it in carbonates, transitioning the atmosphere from the CO2-dominated atmosphere to a nitrogen-dominated atmosphere. And so this has the effect of warming the upper atmosphere, which means that when you go back into runaway greenhouse, as we're seeing here, it's much easier to get rid of the water and the oxygen. With the water mainly. And so what you find when you do this particular sensitivity test is that it's much easier to recover the modern Venus state when you allow for this transient period of habitability. This is, I want to emphasize though, this is sensitive to your assumptions about atmospheric escape. And so this is fairly tentative. To summarize, for Venus, what we found broadly is that both a transient period of past habitability and never habitable histories can be reconciled with atmospheric constraints, surface heat flow constraints, trace gas, radiogenic constraints. So both seem to work. If you believe that having a very CO2-rich upper atmosphere throttles water loss, then you might tentatively favor a habitable past, but really more data are needed here. And so understanding why Venus's atmosphere is oxygen-free and whether it was habitable in the past will require in situ measurements to constrain escape through time, surface sinks of oxygen, and so on. Unfortunately, there are now 3, Da Vinci, Veritas, and Envision, 3 missions to Venus in the next few years that will provide many of these constraints. Da Vinci will measure trace gas and isotopes, better constraining the outgassing and escape history, whereas the orbiters will constrain the tectonic state of the interior, as well as potentially some of the surface mineralogy from near-infrared spectroscopy and imaging. So I'm very excited to see what these missions return. But of course, in addition to the Venus missions, we're going to get a whole bunch of constraints on Venus-like exoplanets in the not too distant future, and opportunities to do comparative planetology. The TRAPPIST-1 system here, of course, is perhaps the most promising case of this, where you've got 2, perhaps 3 Venus analogs that are characterizable, as well as the other habitable zone planets in the system. And just to convince you that this is worth thinking about, there people have done just simulated observations of what these planets would look like to JWST, and it does seem to be the case that you could constrain some of these bulk constituents, CO2, steam, oxygen. It may also be possible to do this from the ground with the upcoming ELTs. And this is just a selection of papers that have done these sort of simulated observations for JWST, all of which have essentially came to the same conclusion that this should work, that at least for relatively clear atmospheres, you should be able to say something about atmospheric composition for these planets. Now, of course, these planets are not quite Venus analogs in the sense that they're being subjected to very different stellar evolution. These small stars have a very extended pre-main sequence, which means these inner planets and all the planets have been subjected to very high bolometric and XUV luminosities for potentially hundreds of millions of years. So this is potentially going to drive key differences in their evolution. But we do have some constraints already on composition. There are, for the TRAPPIST system at least, very good mass constraints from TTVs, which certainly for the inner planets allow you to put a pretty strong upper limit on how much water could be present at the surface, just because if there was more water, it would inflate the atmosphere and change the density of the planet. And so what we attempted to do was to take our evolutionary models, apply them to these exoplanet systems, particularly the TRAPPIST system, taking into account the different stellar evolution and making sure we recovered surface water inventory is consistent with what is these constraints. So here's an example of that, the model applied to TRAPPIST-1e. The colors are different, but it's very much the same model as before. I won't go through all the details, but once again, the energy budget is all important. Now it takes potentially a few 100 million years for the outgoing long-wave radiation to drop below the runaway greenhouse limit. And so you potentially have a very extended magma ocean phase. And so you may have a steam atmosphere lasting for hundreds of millions of years before it eventually condenses out. This is the mantle surface temperature evolution, the water condensing out after the termination of the magma ocean. And of course, we're tracking the redox budget as before, sources of oxygen through that long steam atmosphere phase, and then subsequent crustal sinks to anticipate oxygen in the atmosphere now. And so this is what this figure is trying to summarize. This is the current, what you might generously call probability distributions for the current atmospheric compositions of TRAPPIST-B through G. I didn't do H because the model isn't really set up to do really cold objects at the moment. I put probability distributions in quotation marks because there is, of course, a degree of arbitrariness in how you select initial inventory ranges and things like that. But I think you can still say something interesting about qualitative trends here. So we see interesting patterns in the CO2 distribution, sort of bimodal CO2 distribution or trimodal for these habitable planets due to carbon cycle feedbacks. But the main thing you probably noticed is oxygen in cyan here. The probability of oxygen diminishes as you move outwards in the system. And that's seen more clearly in this figure where we're plotting just the percentage of model runs with very oxygen-rich atmospheres for the 6 planets considered, B through G. And you do indeed see that oxygen-rich atmospheres are fairly probable for these inner Venus analogs and much less likely for the outer planets. The different colors here are just different sensitivity tests, different assumptions about composition, but in general, you see the same trend. I should say, so the main driver of this is, of course, the duration of the magma ocean. One way you can break this trend is if you insist on the low densities of these outer planets being attributable to very large surface water inventory. Then you get a kind of water world scenario, as I described way back at the start, where the pressure overburden of that volatile inventory suppresses your oxygen sinks and makes it much more likely for abiotic oxygen atmospheres to be retained. And you, of course, can sort of apply the model to other eminently characterizable exoplanets. This is the newly discovered LP899 system, or Speculus 2, where we've got one Venus analog shown here, which, even though it's a bit bigger, 1.3 Earth radii, you get model outputs that look a lot like the predictions for TRAPPIST-1b. And then you have another habitable planet in the system where you habitable zone planet in the system where oxygen, the outputs look like a lot like TRAPPIST-1e, where oxygen-rich atmospheres are somewhat less likely. But what is perhaps more useful than these just simple predictions is that you can use these models to try and understand mechanism, to try and figure out what unknown variables are most important for driving atmospheric evolution, possible oxygenation. And that's what this weird looking plot is showing. On the y-axis here, we've got a whole bunch of unknown input parameters. So think initial composition, how atmospheric escape works, the carbon cycle, atmosphere interior exchange parameters, cloud properties. And then for the 6 TRAPPIST planets, in this case, we are plotting every dot here is just a very simple linear correlation between that parameter and how much oxygen you end up with. So the color is just the R-squared value of that correlation, and the size of the dot is related to the significance of that correlation. And so you can immediately look at a plot like this and start to say something about what is most important for oxygenation. You see that for these inner planets, B and C, they're comparatively simple objects in the sense that all that matters is initial water inventory, what is the internal heat production, and how do these dry crustal sinks work. Whereas for these outer planets, it's more complicated. The details of atmospheric escape physics are really important in controlling outcomes, as are cloud properties, albedo feedbacks. I should caveat this though by saying that when you're doing this kind of modeling, there are of course simplifications you have to make, certain emissions, and so there are many processes here that are neglected that we hope to revisit. The possible effect of an initial hydrogen-rich atmosphere is ignored. There's been really interesting work coming out of the Clever Planets collaboration on what controls the nitrogen and sulfur inventories of terrestrial planets. And to me, at least, this work suggests that it might be possible to have really radically different volatile inventories to what we see on the Earth, which is considered here where we're just focusing on carbon, hydrogen, oxygen evolution. We've ignored photochemistry, which is probably fine in terms of tracking just bulk atmospheric evolution, but there are regions of parameter space where the photochemistry could have an important effect. 3D effects on circulation are ignored, orbital evolution, and of course the details of atmospheric escape are poorly constrained. And so there's a lot of room for improvement here. And if you're a prospective graduate student interested in working on some of these problems, do feel free to reach out. But my hope, at least, is that this model and this kind of modeling is a first step in trying to develop some testable models of terrestrial planet evolution to be able to go after biosignatures. And so this is, just to finish, a really quick summary of what the next few years could look like, in the sense that we will continue, of course, to learn more about Venus and Earth's evolution, but are additionally going to get atmospheric abundances, constraints on a number of terrestrial exoplanets. Here are some made-up possible constraints here. And so we can hope to leverage these kinds of evolutionary models to both predict and then make sense of the atmospheric observations that we see. You can kind of imagine an iterative process where observations inform model development and vice versa. And of course, I put my model up here, but this is going to require an ensemble of models to really understand this evolution in a rigorous way. But my hope is that if this is done, we can get to a point where down the line, if we make some observations with a LUVEX-like telescope of something that has promising biosignatures, oxygen, perhaps methane, we'll have built the broader understanding of rocky planet evolution and oxygenation, redox evolution to interpret this potential biosignature in a more nuanced way, in a more rigorous way. So with that, I think I'm at about 45 minutes, so I will just leave up my conclusions here and say there are, if you're interested in knowing more, there are papers on the various subtopics I discussed today. And yeah, thank you again for the invitation. I'm very happy to take questions.
Great, thank you very much. Very interesting talk. Now we'll open the floor to questions. So if you have questions, you can type them either in the Q&A section and then we will read them, or you can also, as Raj is just doing, raise your virtual hand and you will be called to ask your question. So go on, Raj.
Hey, great talk, Joshua. Quick thing, just so that I understand clearly, when you are calculating O2 pressure in the atmosphere, especially, I guess, during the magma motion stage or even subsequently, what are you doing in terms of redox that are in silicates? Like, are you kind of consistently tracking, like Fe3 plus total iron ratio of the melts? Or, I mean, are they consistent with what one would expect? Or even in a solid state rocky bodies, are you calculating like again, crustal oxidation and stuff?
Yeah, sure, I can try and summarize that. So during the magma ocean, the assumption is that the atmospheric oxygen is just in equilibrium with the oxygen fugacity of the melt. And so we are tracking both ion speciation in the magma ocean, ion 3+ to 2+ ratio, as well as the total oxygen inventory and how that's partitioned between that melt phase and the atmosphere. And we just adopted the Krissansen-Totton parameterization of relating ion 3+ to 2+ to oxygen fugacity. So that during the magma ocean is purely an equilibrium partitioning. Once the magma ocean freezes, it becomes a source sink balance. And so there's just some inventory of atmospheric oxygen that is being added to through hydrogen loss, and then oxygen is being removed through crustal processes that depend on the rate of melt production. So the rate at which hydrogen and carbon monoxide are degassing is tied to both the composition of the mantle and just the rate at which you're producing new crust. Does that broadly explain how?
Yeah, thank you. Thanks.
Right, we have a question from Sukrit Ranjan, who says, thank you for a very great talk. For the Venus validation cases, are you able to convert the dry crustal oxidation efficiency to a deposition velocity for O2?
I haven't actually done that calculation. It'd be interesting to compare. So essentially what you find is you need dry crustal oxidation that's sort of part per 1,000 or better in terms of the fraction of new crust that gets oxidized. And so that can kind of be compared to different possible mechanisms to assess plausibility. But yeah, it will be interesting to do direct sort of photochemical comparison.
Okay, I had a question also about about the Venus validation cases. You say that there might be a possibility to have previously habitable Venus when you had CO2, which was promoting escape, but in my understanding, CO2 was on the contrary creating a cold trap, which was slowing down the escape. So is that a different mechanism, or?
Sorry, could you explain the?
Well, so in my understanding of the effect of CO2 was that it was creating a cold trap, which was really an obstacle to diffusion of hydrogen species like water. So I was wondering whether, in your case, that was some were working in a different way.
So I guess I probably skipped over the fact that there are two different tests there, the kind of nominal model where we don't try and relate the upper atmosphere mesosphere temperature to atmospheric composition. We just assume a particular or sample a range of isotherms and just that the equilibrium temperature of the planet and say that there's no feedback. And that's the nominal case I presented with the two scenarios for recovering Venus, the never habitable and habitable. But I additionally showed a sensitivity test where I said, suppose that isn't true, suppose that the CO2-rich atmosphere, having a CO2-dominated upper atmosphere cools the atmosphere, enhances the cold trap, then you get a different outcome where it's you essentially have to pass through a habitable phase to recover modern Venus. So hopefully that that makes more sense now.
Yeah, I guess it does. All right, so do we have other questions? Well, I did have another one actually in the meantime. So I guess the cycling of carbon in your model is parameterized in something similar to plate tectonics, and whether it was, because in general we sort of think of that a planet will either undergo plate tectonic or stagnant lid. So is your model sort of self-consistently recovering the transition from one state to the other? Well, not that we actually understand how this transition occurs, but is it something that your model is?
Yeah, that's a good question. So the nominal model is just plate tectonics. For Venus, of course, that's not a reasonable assumption. So I changed it to allow for a stagnant lid mode. But I was not trying to anticipate or capture that transition. I just allowed the time at which Venus transitioned from a plate tectonic regime to a stagnant lid to be another free parameter. Say that happened at some point in the past, either very early on or more recently, and then looked at the consequences of the timing of that transition for the atmospheric evolution. I didn't show those figures because it didn't have a particularly dramatic effect. There was some an early transition is let me see if I have that result here actually. I find that slide unfortunately, but yeah, by and large, it didn't have a huge impact, but an important caveat to that is that the carbon cycling was not done self-consistently in a stagnant lid. So that needs to be revisited to see if the effect of the stagnant lid on the carbon cycle changes that picture.
Okay. And we have an answer to your answer by Krissansen-Totton, who says that such calculations is relevant to work I'm doing with Eddie, what he's doing with Eddie. And he says, let's talk.
Yeah, sounds great.
Right, other questions before we end the seminar? Yes, we have a question by Vladimir Aypetin, who is now allowed to talk.
Yes, hello, Josh. Thanks for a nice talk. So I have a question about, evolution of nitrogen. So you haven't mentioned anything about nitrogen. So I see that you're talking about carbon dioxide, water vapor, right, and oxygen, but not nitrogen. What and we know, and the current Venus we have nitrogen amount in kilograms 3 times more than we have on Earth. So how would nitrogen change all the scenarios of the atmospheric evolution?
Yeah, so the way that it would obviously be better to have a nitrogen cycle in there explicitly, but the way I attempted to do things in this iteration of the model was to just track carbon, hydrogen, and oxygen and have some fixed background of nitrogen, I think 1 bar in most cases. But then I repeated the calculation for different background nitrogen inventories, I think 0.5 bar, 3 bar, and showed the difference in how that affects the evolution. And generally, it's a fairly subtle change in atmospheric evolution and redox evolution. Of course, you can imagine exceptions to that. If you eroded away all the nitrogen, then that's obviously going to dramatically change the prospects for habitability and climate evolution. And so that's something that's harder to capture. I did, for kind of the TRAPPIST calculations and some of these highly irradiated exoplanets, I did allow for a pretty substantial non-thermal escape flux, not explicitly eroding nitrogen, but eroding the other atmospheric constituents, and then noting when the atmosphere as a total starts to get down to pressures where you might lose the entire atmosphere, less than a bar. And so that gives you a very crude way of assessing whether these atmospheres are likely to end up completely eroded. And again, I didn't show that plot, but you find that for the inner planets of, say, the TRAPPIST system, there's maybe a 30–40% chance of that occurring, whereas for the outer planets, you do tend to retain fairly substantial atmospheric inventory. So yeah, it's kind of a long-winded way of answering your question. Nitrogen is an explicitly model. We did do some sensitivity tests as well as the sensitivity to total atmospheric loss for these highly irradiated planets.
Thank you.
Oh yeah, so I was muted. So Claire, you can ask your question.
Thanks. Okay. Hi, Josh. Great talk.
Hey.
I have a more kind of general question, which is, are you able to pick out from these kinds of models that you've done any dominant, like emergent parameters that would mean if you have a young planet that's forming in the middle of the habitable zone somewhere, if it's more likely to turn into an Earth or into a Venus, or is this just way beyond kind of the capability of writing models?
I wouldn't say it's something I've sort of explicitly thought about, in large part because so much of whether you end up with an Earth or a Venus is dependent on the cloud feedbacks, the albedo feedbacks that dictate the climate evolution, and that's not something that I've tried to explicitly model. I've instead said, suppose the albedo is blah, then what are the consequences of that in terms of the geochemistry and the redox evolution? And so I think that's less well suited to sort of anticipating future habitability, but and more geared towards exploring the consequences of particular albedos. Yeah.
Cool. Okay. Yeah. Thank you.
Right, now is your last chance to ask a question to Josh. Right, well then, I guess we'll close the seminar here. Thank you very much everyone for attending. Thank you, Josh, for giving this great talk. And yeah, see all of you in 2 weeks for the next seminar.